Hi. So I'm Lennart Poettering. I worked on systemd and a couple of other projects. Today I'd like to talk about specifically containers in systemd. It's an area where we have been working in for the last year or something, and I kind of want to give an overview in what we're precisely doing there and what's currently viable and where the road will go for us in that area. It's probably going to be a very technical talk. I hope it's not going to be too technical for you. If you have any questions, just ask questions right away. I much prefer being interrupted and we can have a little bit of a discussion going on here than me just taking questions in the end. So yeah, don't hesitate if you want to know details about something. Yeah, containers. Let's get started with that. So containers, you know them, like I figure the most well-known container implementation these days is Docker. Then there's Rocket, which is something, it's kind of the same thing as Docker, but it's by a different company, it's by CoreOS. There's some friction between Docker and some other companies, so they, CoreOS decided to do their own thing. There's LXC, which is an old implementation. Actually, Docker traditionally used LXC as backend. There's libvirt LXC that not too many people know, I think, which is like a backend for libvirt thing. There's LXC. There's OpenVZ, which is like the free version of Virtuoso. Kind of what I'm trying to make the point here is there are many implementations of that, and of course then the question is, why do we need another like implementation of container features if we already have so many? So what I specifically want to talk about is the systemd nspawn plus systemd machined plus systemd importd combination that we are shipping in most modern systemd versions. What I'm talking about here is mostly like really recent systemd versions. So it's not the systemd versions that you'll find in the distributions that are already released. It's not what you will find in RHEL 7 or new CentOS or things like that. But it's a thing that will be in the next big releases of the big commercial distributions. Yeah. Systemd nspawn has been around for a while. It's a very minimal implementation, right? Like, you know, Docker and Rocket and LXC, like there are these big add-on projects that you install on top of your Linux distribution. They add fundamental new complexity, like new concepts to it. For us, nspawn is a very minimal thing. It's like the binary that this container manager used to be something like 200 lines of code. Nowadays it's more like 1,000, but 1,000 is still pretty much nothing. And there are two other components that I'll talk about in detail as well. So why do we even bother, right? Why have all this in systemd? Because I mean, let's recap what systemd actually is. Systemd started out as purely an init system, right? It is purely a binary for PID1. And then we noticed that, well, it's not done with actually having a PID1. If you want to bring up a system and maintain it, you need a couple of other components as well. So we added a couple of other things that are basic building blocks of the OS. And that's kind of what we then define systemd as being a set of basic building blocks to build an OS from. So we're not a product. We're just something that other people can build a product out. And we think that in systemd everything belongs that is on the low-level user space side of the operating system that just has to work and that is otherwise not interesting usually on its own, but it's interesting so that you can build other really interesting stuff out of it. So we believe inherently that operating system, that containers should be part of the operating system concept from the ground up. Right? We believe that a modern operating system, how it should look like, should come with containers built in, that everything that you run on the operating system should be containerized, and hence the entire concept of a container should not be something that you add on top, but something that the operating system comes, like knows from its deepest core. The inspiration for this is actually not Docker, LXC, or these other kind of things. The inspiration for this is really Solaris zones. I'm not sure if anybody of you ever used Solaris. Solaris is like this classic Unix system and it has a zones concept. The zones concept basically allows you to partition your system into a couple of different, mostly separate machines. It works a little bit like VMs, except that it doesn't virtualize hardware, so the density of virtualization can be much, much higher. And the level of integration can be also much, much higher. So that's kind of what we're going for, right? Like, so to underline that again, I have no interest at all in being in competition with Docker for these kind of things. I just believe containers should be part of the OS, and Solaris Zones is how we think it was nicely done before. So what does this effectively mean for what you run in containers? We believe that the kind of containers that we try to care for, they should be running an OS inside that is very similar to the OS that runs outside of the containers to manage the containers from the outside. So this is different, like, for example, for Docker, right? Docker focuses very closely on apps, like they want to run an Apache web server and nothing else in the containers. We say a comprehensive API must consist of more than just really the individual servers. We should add, to a certain level, the basic parts of the OS to the container itself, so that we know, so that the interfaces between the container and the rest of the system are minimal, so that the containers stay portable as they can be. So yeah, this basically means that, effectively means that inside of the containers, we run a logging system, as well as we run one outside of the containers, which is opposite to Docker, right? Docker runs pretty much nothing inside of the containers except for Apache itself or something like that. We go for something that we call integrated isolation, right? Like we say, on one hand, we want isolation. On the other hand, we want integration. We want isolation so that the runtimes, the API runtimes and these things like that, are isolated from the host OS so that you can update things separately, that you do not enter DLL hell and these kind of things. But on the other hand, we care for integration. Integration meaning that the stuff that runs inside of the containers and the stuff outside of the containers should appear to a certain level integrated so that the administrator does not always have to keep in mind, like pretend they were completely different machines. What does it effectively mean? We'll have some examples in the end. But it could mean, for example, that logging, the view to logging is unified, right? So that you can say, okay, I want to see the logging of my machine, and then it will contain the logging of all the individual containers plus the logging of the outer machine as well. But yeah, that you can merge the stream into one linear thing instead of having multiple different ones, if you want to. Of course, I mean, the other option is, of course, to look into the individual containers if you want that. But yeah, this is kind of what we try to go for. On one hand, isolation, specifically when it comes to APIs and things like that. On the other hand, integration, so that the administrator actually still gets a unified view on the system, wherever that's possible. So we also believe that many of the features that containers provide are actually something that the host should also have, right? So this could mean, for example, if you use Docker, right, then, and if you ever played around with Docker, you know this feature that they have where you can basically make snapshots of Docker images, right? Like you can, I mean, if you ever looked at a Docker file, it basically says do this and do this and do this, and then it saves the version away, and then you do the next thing and saves the version away, and these kind of things. So we believe that that's a nice feature, and containers should provide them, but it should not only be containers that provide them, it should actually be available for the host system as well, right? There's no reason in the world why doing these kind of things should be specific to containers. It should actually be the entire system that's built like that, right? Meaning that if you install a system and you configure something, that you can save everything, take a snapshot of these kind of things, replay them, that you have atomic updates, that you can return to the old versions, that you can replicate these things to other machines, and that they are running exactly the same way as they were originally, and you have the same files on disk. Because containers give you that, and the host system so far didn't. We believe the host system should provide that as well. Another thing that we try to focus on with our container stuff, it should really be minimal. So the minimal basically means is that we will not give you as many options as many of the other implementations. We will not solve as many problems as they will solve. Like, for example, all the orchestration stuff we will kind of not focus on. What we, however, focus on is that the that the stuff that we do is minimal, that the code paths are simple, and that our focus is really on getting the lower level parts right? So we care more about doing something right for the long run, rather than being able to deliver something very, very quickly that might not be right. This is, I mean, it's a luxury that we have, because we know that people who want to use something today, they can use Docker and everything's good. But we can kind of fix these things properly and build them into the core operating system at a slightly slower pace. However, we'll eventually, hopefully, have the, as we believe, simpler and more correct implementation of things. So our philosophy is like, it's actually with the rest of systemd the same thing. We want no hacks in our stuff, right? Like, we will not work around around problems. We will fix the problems, right? So we want a clean, integrated implementation. Specifically here, that one example, like if you think about containers and these snapshotting and these kind of things, then you want some support in storage for that. They're like Docker doesn't really make a decision about that. Like, traditionally they used AUFS, but there are implementations that use it on Btrfs, there are implementations that use it on LVM, there are implementations that use it on ZFS. So they will not make a decision. They basically support many different options, and most of them are badly maintained. However, we don't want this these half worked out solutions. We want one that works for everybody, and we believe that it should be the technology of the future that we support there, because we see systemd as being something where we develop software for the future and not for the past. Specifically for us, one example is Btrfs, not LVM. Sure, Btrfs is not stable right now, but like conceptually, at least for us, it's very clear that LVM is not the future of storage, but Btrfs is much rather. So with the rest of systemd as well, we kind of have this focus on, yeah, we will work on all file systems, and if you use LVM, everything's great. But we will provide you with additional features if you use Btrfs, right? Like, especially snapshotting, things like that. This again, very important to us. We believe that the stuff that runs in the containers should get a really well-defined execution environment that is really, really close to how the app would actually run if it would run on bare metal outside, right? Specifically, this means all kinds of smaller details, like things that Docker in many ways does not get right. Like, it starts from obvious, like superficial things, like how is cleanup and /temp handled, right? Like, we believe it should be the same thing if you run a container, if you run a host. /temp should be automatically cleaned up how it's nowadays done. It means that you have your own logging stuff in the container and on the host, and should just work the same way. It also means really low-level execution environment things, like, for example, that if you execute it inside of a container, you get zigterm to be shut down, and on the host, you get zigterm for being shut down, and it's not different, which something, by the way, which Docker doesn't get right. Anyway, and the other thing is that for us, we have no intention to like own this stuff. We always care about the open doors for the alternatives. That basically means that much of the integration that we have with the containers in systemd that we'll talk about later is actually open for any kind of implementation that you want. Specifically, this means libvirt LXC, for example, is nicely integrated in systemd as well. We'll come to some command lines that basically then work with them and work with us the same way. So it's really like if you use nspawn, which is our implementation, then good for you, and we of course will help you with that. But if you use something else, you can get this almost the same level of integration as well. Something else is we kind of want to avoid defining new standards where there already are standards. This is specifically, you could say, if you have, how do you actually distribute the containers to people? We believe there are already pretty well-known ways to do that. One is a tarball, the other one is a disk image, and we should support those, right? And then hence systemd nspawn and all the stuff that we have created there will actually, is able to run disk images directly, right? It feels a little bit like how you would point KVM onto a disk image. You can do the same with nspawn, and we'll disassemble the GPT partition table or whatever you have in there, find the file systems to mount them, and boot them. So that you basically get some level of portability of the images between, like, virtualization a la KVM and virtualization a la containers because systemd nspawn will eat whatever you point to it. So for us, it kind of, we say we should not define any new storage standard if the existing ones, which are disk images and which are tables, work fine. This is like if you compare it again with something like Docker, for example, they created their own image format, which is based on AUFS, their own metadata and these kind of things. We believe that there's no really strong reason to have your own stuff, and you can just use what's already there for distributing normal machines and normal things, as mentioned, the tables. Then something that I would also like to mention is, for us, containers matter a lot. Simply because that's how we actually test systemd, like the entire rest of systemd, every day. Because, you know, systemd, after all, like, boots up your system, right? So basically, every time you test it, if you don't use something like containers, you would have to reboot your physical machine, right? And then I would sit there in front of my laptop and keep hitting reboot on the physical machine. And of course, I would lose a lot of time. That would not be fun. Hence, I mean, it's actually the reason why nspawn was created in the first place. Because we said, okay, we are writing an system. We want to be able to test this. So how do we do this? Okay, we use a container for that. And we looked around and figured out that the container solutions were all so complex back then that we didn't really want to deal with that. So I sat down and wrote nspawn, which again used to be this 500-line program, which was good enough to actually run our init system and simulate enough from the system so that you can actually, most of the time, just stick to that to test if your system still boots up and everything's managed nicely and everything works correctly.
Question. If you test systemd only in containers?
Well, not only in containers.
Sometimes don't catch real-world problems that can occur on real hardware.
Sure, I mean, again, we don't test it only in containers, right? But we test this more often in containers than not. Simply because, I don't know, if I have some problem with the dependency logic in systemd, I'm pretty sure that it will work the same way on a real machine as it will work in a container. So,
that's optimistic.
well, I mean, we do test regularly on physical machines as well. We also test on KVM regularly. And Fedora, like who usually get our new version the quickest, they do have their own level of testing then again. So yeah, but for us, I mean, and the other thing is like, it's not just about that containers are so much quicker. It's also you can attach a debugger to them, right? Because you run your host, where you can have your debugger, and then you run the container, which runs systemd inside of it. You can just attach GDB from outside to the container, and you can actually look what's actually happening. So that's awesome. So to also make clear what's not in focus, wow, that's an awful typo there. What's not in focus is cluster-wide orchestration and these kind of things, which is something that Docker and these things are kind of focusing on. We will not write you the middleware that actually does HTTP, like is a HTTP application server that manages Docker containers across a network. That's not really our focus. We are low-level people, right? So we will serve you the low-level stuff, and then people can write something on top. And I think about much of the stuff that we provide there, it makes a lot of sense to build something on top. In fact, Rocket, you know, this thing that CoreOS is doing, is using that. They're making use of nspawn. They're basically, for the actual containerization that they're doing, they simply run nspawn because, I mean, there's a lot of things that we did for nspawn over the years that you just don't want to throw away. You don't want to start from fresh. So Rocket goes the right way, we believe. They just take this lower level bits that we have, add some fancy stuff on top to actually solve the actual problems that many people have with maintaining clusters. So much about the background of why we're doing this and where it fits in and why it's not just yet another re-implementation of containers where there are so many already. So let's focus a little bit more about the actual programs. But first, let's have some more questions, I think, if you have any. You should need to ask more questions. I mentioned I want to have a good conversation with you, not just me talking here. Anyway, if there are no questions, then let's proceed. The first set of tools that I would like to point you to is actually not systemd nspawn, which is the real container manager, but something called machine control and systemd machined. Systemd machined is basically a very minimal daemon that runs, like, it's bus activated on systemd system, so it's normally not running until somebody actually asks for it. And it basically allows you to register VMs and containers from your manager with it. So we use the word machine usually in systemd as an abstraction for VMs and containers. Like we were looking for some abstract term that can reference to both concepts. So we call that machine, and hence we call the daemon that registered as machine D. Any container VM manager can register with it. Many do, like libvirt, LXC, and these things do. LXC does, and these kind of things. And by doing that, you get a lot of integration into the rest of the system. Like, here are a couple of examples. System control, system control is like this primary command that you use to interface with systemd. It has this -m command switch. With -m, you can specify run what I just specify here, but run it within this local container. System control -r is a similar command. It basically says, yeah, do whatever I'm saying you to do, but run it recursively down the tree into all the containers that are on the system. So you can basically list something, and you get a list of the servers that run on the host, the services that run on each of the containers, and you can basically get a symbol list that gives you an entire idea about what's running in the container. And as mentioned, all of this works regardless which container manager you use, as long as it registers with systemd machined. System control list machines is another command. Basically just gives you a health report. Like, it will just give you a list of the machines and the health report about the service managers that run inside of it. So it's different from what I was saying before, because it will not actually tell you anything about services. It will just say you, yeah, that system is healthy, or that container is healthy, and that container is unhealthy, and things like that. Login control -m, like, basically we added these -m switches to all our tools. Login control, not sure if you know that tool, it's basically, it gives you a list of who's logged in, what seats are there, and details about that kind of stuff. It's like multi-seat aware and these things. It actually has login control -m, meaning you can actually query that for any local container. Journal control -m is the interface. The journal control is basically the logging interface that we have in systemd. Journal control -m allows you to get the logs from any local container you like. You specify the name after the -m, and there you have them. Journal control -m is about merging the logs. So it will not only show you the logs of one specific container, but of all the containers, and merge them into one stream. I mentioned it earlier. But it doesn't stop there. It's also, through the registration, you not only get all the, there's actually a lot more integration in systemd as well. This is just a couple of examples I came up with. But even outside of systemd, there's lots of integration making use of this. For example, PS, the classic PS command that shows you the processes on Unix system. And since 2 years or something, PS will actually show you the machine name as well. So if you see all the processes on your system, you just wonder, like, that process, to which container does it actually belong? You can just specify that as a special column in PS-EO, and will show you to which machine a process belongs. GNOME System Monitor has been hooked up as well. GNOME System Monitor, in many ways, is kind of the UI version of PS, I guess, and hence it made a lot of sense to hook that up. And there's a couple of other tools that support this. Then here are a couple of more specialized tools. There's the question.
My question is actually not very technical, but your answer may very well be more technical than the question. Of the features of this stuff which are already implemented and straightforwardly usable, which, in your own opinion, are the coolest, and of course why?
Well, I guess the one machine control login is probably kind of cool. But let me quickly talk about the last line that I just shown there.
Sure.
These are kind of, like, the upper ones are kind of obvious things. The lower ones I think are much nicer, because you can actually turn them into really powerful stuff. Systemd run -m is basically systemd run is basically something how you can run arbitrary commands as a service. So it works on the local system, where you can just say systemd -run, you specify a couple of parameters, and then it will be run in the background as a service in a very encapsulated way. But it also has systemd run -m. With the -m, you can specify a container name, and then it will run something inside of those containers. And all that's necessary for that is that those containers have been registered with machined, like all the interesting ones do. and that inside of the container you have systemd, because I mean, if there's no systemd inside of it, we cannot talk to it. So this is kind of cool, because with systemd run you can basically say, yeah, execute this command in that container and that command in that container, and you can basically write really nice script that go into the individual containers, execute specific code there. Machine control login is kind of related to that. It actually gives you a login in any local container you want. It will give you a new login prompt, which is actually really, really useful. Because it works with anything. Like if you run an LXC or libvirt LXC container or something like that, you can just type machine control login and there you get another prompt. And you can have as many prompts as you have, and you can exit from them again and things like that. It's kind of cool. Machine control stop is kind of boring. Again, it will shut that down. But I think I personally like systemd run the most. Coming back to your original question. Any other questions at this point? Oops. Something else. Simply by registering with machined, what you get is actually automatic host name resolution. So this uses, I'm not sure if you know the concepts of NSS, but basically this makes sure that if you reference a host name from the machine, like a container name from the machine as like ping host name or SSH host name, then simply by registering with machined on the local machine, all the local container names are resolvable. So if you have a container called foobar and you type SSH foobar on the container host, it will just work. It will do what you expect. It will connect you to that thing. It's actually really, really powerful and just works. No further action required. All that's necessary is that your container VM manager registers with machined, which, as mentioned, most of them do. That's actually kind of a cool feature as well. But this is not only about tools like that admins will come into contact with your users. This concept of opening up containers to the OS also goes down into the APIs that we provide. One example is being SDBus. I'm not sure if you have followed the KDBus discussions currently on LKML. SDBus is our little implementation of a bus client library, and we focus to make it really, really useful. And one thing it will do is it allows you to connect to the bus, to the communication bus of any local containers. It just has a high-level call where you specify the container name, and then you get the system bus of that container instead of the host. Of course, what I'm just saying here, you actually have to need some kind of understanding of what dbus is. Sorry if you don't, but it's actually really, really powerful if you're a developer. Let's summarize it as that. Anyway, what this hopefully shows you is that this integration is really useful. This is just a couple of examples in different areas, like some in systemd, some outside of systemd, some more for the admins, some for the developers. What you get through that. This kind of integration is not new. As mentioned, we tried to get inspiration there from Solaris Zones. Solaris Zones had this kind of integrations 15 years ago, where they basically, their system control equivalent was called SVC control. And SVC control had this kind of recursive go into the different zones as well. So this is not new, and I will not claim it is new. We just think Linux should have the same level of integration there. Next one. So that's machined. Now let's focus on systemd and spawn. Systemd and spawn integrates into machined as well, but systemd and spawn is basically then just the one container manager that we ship. It's relatively simple. It's just still one C file, but it's also very, very powerful, and it can do many, many things. This systemd and spawn is basically an alternative to the actual LXC, for example, except that in systemd and spawn the focus is on the command line, and the focus of requiring as little configuration as necessary. So if you run a systemd and spawn, you can just pass it a directory, and it will boot it up, right? That directory should include a disk image, so it basically should have user and lib and etc in these kind of directories. And you pass that to systemd and spawn with uppercase D, and that's already enough. It will boot it up. We can actually, if we still have time later, we can show you that in a demo. You can even have it more easy if you just put your container images into valid machines and just put the directories, like the root directories, in there. And then you can type systemd and spawn dash uppercase M and just specify the container name, and will automatically find it. It can alternatively, I already mentioned that a bit in Van earlier, it can actually disassemble GPT partition tables and actually even MBR partition tables. So basically, if you have a raw disk image, like for example, one that you want to boot up with a VM, with KVM or some other virtual machine manager, you can also pass it to NSpawn directly, and NSpawn will try to do the right thing. It has a different boot process though than as a VM. So a VM will try to find the boot sector and boot through that. This code will, however, instead either look for properly marked GPT partitions, or it will look for the only Linux partition there is on that image, which makes most of the images just boot. But given that it is a different algorithm than actually booting them in the VM, some images are not bootable with NSpawn. Yeah. Systemd NSpawn is designed, so it's actually, with every invocation of Systemd NSpawn, you run one instance of a container. So that's very different from Docker or these other kind of things where you have a central daemon that forks this off. For us, Systemd NSpawn is really like you can either run it from the command line, or you can run it as a service. And then literally you can run it container as a service, where we provide you systemd-nspawn add.service, and sure, like that thing that you see there is kind of only makes sense if you actually have experience with systemd in some way. It basically is a templated service. I don't think I should go into too much detail now what that is. But basically means that, yeah, for us a container is managed by systemd in the very same way as any other service is maintained. So if you run Apache on the host, or you run an entire container on the host, same thing for it. You can explore it the same way, see the process in the same way. You can even do resource management the same way, right? Like for any normal service, you can use system control set property, and then you can specify the service name CPU shares equals 100, and that basically means that this service shall be lower scheduled. And in this case, because we use systemd-nspawn at foobar, we do this for a container. It's the exact same thing as if you would do it for Apache, where it would call apache.service or httpt.service. So the point I'm making here is systemd-nspawn is super simple. It just exposes containers the same way as normal services are exposed to the rest of the system. So that much about systemd-nspawn. If we have the time, I can show you how that actually looks like if you run it. Let's focus on one more component, systemd-networkd. Systemd-networkd is something that we have been working on that is supposed to manage the network. Now, you might wonder, what does that have to do with containers? Like in a way, you could say that systemd-networkd is a bit like what Network Manager was supposed to be but never was. So it's a very minimal, low-level-ish network management solution that can react on hardware coming and going, link beat coming and going. But in contrast to Network Manager, it's actually suitable to run in very minimal environments. Like embedded devices, like you find a lot of embedded devices already that use it. Like Intel is even building a real hub out of it, like a real network hardware device that they sell. But networkd also runs in the initrd, like in a very early boot environment and things like that. And it runs really well in containers. And that's actually really useful there because it has container support by default. So networkd, like the concept of configuration of networkd are really much more interesting than the ones of Network Manager, because you can, like as an admin, write down configuration and say this configuration applies to all network devices that ever show up that match these properties. And these properties can be MAC address, can be name of the interface, can be all the kinds of things, which allows us to very nicely, with one configuration file, express on one side when networkds run on the host, then, and the new VETH, I'm not sure if you know what VETH is, but it's a virtual Ethernet tunnel that basically is used between a virtual container and the host. When a new VETH tunnel interface shows up, that is pointed towards a container, then it will automatically pick an unused IP range for it, run a DHCP server on it. The DHCP server is actually internal. It's very minimal. DHCP serving is actually one of the simplest things that we can do. Most people will be surprised by that, but actually implementing a DHCP server is much simpler than writing a DHCP client. So anyway, it will do DHCP server on it. It will do IPv4L, that's IPv4 linked local addressing, and it will do IP masquerading, right? So it basically does everything so that what runs in the container can get access to the internet and will just work. It'll just get connectivity like one would expect. If network D, on the other hand, is run inside the container, then it does the reverse. If it sees a tunnel that points to the host, then it will automatically run a DHCP client on it and will also do IPv4L. Meaning, if we run network D on the container and on the host, you just get connectivity out of the box. There will no configuration necessary. It will just do this automatically. And actually, the same algorithms work if you run it in VM, if you run it on container, like this kind of explains to you, or run it in any other way. So, yeah, this is kind of this container support we built in network D by simply saying, yeah, we ship this configuration by default so that you don't have to configure anything. If we execute, you notice that we executed exactly in that environment, we'll do the right thing. Next thing is systemd resolve D. It's a relatively new component of systemd that is not very well known yet. It's like we added that. Resolve D basically deals with DNS name resolution. DNS name resolution is also like mapping a host name to an IP address. Traditionally, this was done by glibc itself. It's basically what's behind the get host by name calls and get address info calls if you ever sat down and did low-level Linux development. Traditionally, these were done in the libc, but it has problems for many reasons, and so we sat down and actually started writing something called systemd resolve D. The main reason we wrote it is so that it can actually coalesce, like merge the DNS zones that are attached to different interfaces so that we can do VPNs nicely and things like that. But actually, I don't want to really talk about that part of it. But what it actually also does, it implements LLMNR. LLMNR is linked local multicast name resolution. LLMNR is something that Microsoft came up with and has been supporting in Windows since 15 years or something. It basically allows that on a local link, like on a local Ethernet link, for example, the machines that are on it don't have to register the names in a real DNS or anything like that, but can still find each other by their names. The idea for them was basically you put your Windows 98 host and your Windows 7 host into the same network, call one foo and the other one bar, that you can just type ping foo on the bar host and ping bar on the foo host and it will just work, right? It's a protocol. It's a very, very simple protocol, and it has been implemented, as mentioned, since Windows 98 or something, and works very, very well with our current versions. And we say, okay, that's actually a useful feature. So we can actually use this in a container scenario. Because if you have the container there and you have the host there, or you actually have 5 containers there and the host there, and they have individual links, then we can use that so that the containers and the host find each other by their names, without actually ever telling the containers explicitly that there's a host by that name, right? So systemd resolve D will, by default, make the local names resolvable, and because normally the containers are directly linked with the host, they can then talk to each other. This kind of is on top of what I already mentioned earlier, where simply by registering with machine D all the local container names resolve. This one will actually do the other way as well, right? So that the containers can ping the host under the host's name, if you still follow what I'm babbling here. And the nice thing, it's not a Linux-specific thing. It's not in any way specific thing to our implementation here. It's exactly what Windows does as well. So if you actually would run a Windows virtual machine instead of a Linux container on the host, the name resolution works the exact same way, and the Windows virtual machine can ping the host under its real name, and the host can ping the Windows machine under its real name. It's kind of cool. So yeah, we register host name by default via this LLMNR protocol, regardless if we run a container and host, and hence they can do name resolutions on both sides. So if you put this together, systemd network D and systemd resolve D, then you have, without any kind of explicit configuration, if you run them both in the container and on the host, they will get the networking right. They will connect everything to the host, to the internet, and they will do name resolution on top of that. So it's kind of a comprehensive solution in that way. And it even works like in a more powerful way, so that you can, for example, say, I have 7 containers here, and one of them runs Apache, the other one runs MySQL, the third one runs my application server, and so on, and I want them to be in a virtual circuit. You can, like in a virtual Ethernet that includes all the 7 containers plus the host, then you can just configure that, and LLMNR will just scale with that. It will provide the names to all of the hosts, and they can talk to each other individually. So yeah, it's a really powerful thing, and as mentioned, it requires no configuration; it will just work. So then let's look at the last component of that I want to talk about, which is systemd importd. It's very new. It's basically, I mentioned that what systemd nspawn ultimately boots is a directory in varlib machines, right? But how do you actually get this stuff into that directory? Like, how do you get a disk image like a /etc/user/lib/temp kind of file hierarchy? How do you get that into varlib machines? And that's where systemd importd comes in. So, of course, it's easy to get them in there. Like, you can download them from the internet as a table, untar them, and there you go. And that works fine. What importd is supposed to do is make that easier for you. So importd is kind of this thing which automatically downloads for you GPT or any other kind of raw disk images or tables. We'll download them and put them in varlib machines so that nspawn can then boot them. It can also be used to then export, like after you made your changes to your local container and varlib machines, and you added a couple of configuration files, did this and that, added a user, and so on. You can then also use importd to export this back into table or back into raw disk image. And then there's also a way how you can import a local table that way. It tries to be very careful with what it does, so it will do all these kind of things that you don't want to know about, like sparse file reconstruction things. It will also, if you download things from the internet, will also do GPG verification of the images. And that's actually really useful because many of the big distributions nowadays already provide online disk images that can be made working this way. Like Ubuntu has a directory like where what they call cloud images, where they ship ready-made tables of installed minimal cloud images. Same thing for Fedora. Fedora doesn't provide tables though. What they do provide is the raw disk images. So you can just download them and boot them in nspawn, and they will just work. And the import tool will actually verify that they are signed with the Ubuntu key or the Fedora key, depending on which one you downloaded there. So that's actually kind of powerful because, yeah, we didn't define any new format. We didn't have to create any kind of infrastructure to prepare these images and get them up on the internet. We just used the images that the distributions provide anyway and just make them workable in the nspawn container. So the formats are tar and raw. There's also some support for Docker images, because, I mean, we realize, of course, that most of the container images in this world are not simple tables or disk images. They are usually in the Docker format, so we provide some import support. We call it DKR, though, for trademark reasons, because Docker is not nice as a company regarding these things. So to give an example here, this is one command line where you, there it is. Machine call, you set a raw disk image, we turn off verification in this case because the Fedora images do not properly sign their stuff right now, but this is hopefully going to be fixed soon. You specify the URL, in this case it's a raw file that is exec compressed. Machine control will actually automatically decompress that and make that available. And then you can boot it up with systemd nspawn-m. And it actually works. So that's systemd importd. Here, that's the systemd nspawn line, basically. So what the first line did is, where's the dot? There's the laser. So what the first line does, it downloads this and places under the name Fedora cloud-based blah 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 into varlib machines, and then this second line here will then execute that, and you will see the boot up screen immediately before you, and you can actually log in, and it will just work. We might actually, like, if the internet is good enough, we can try that, but it's probably one of those demos that will go horribly wrong because the internet's not good enough. So I might not actually do that. How much time do I actually have? I got like 12 minutes left. So are there any questions right now? Otherwise, I will do this slide. No question. There's a question.
How is that actually different to the LXD from Linux containers people?
LXD or LXC?
LXD, the
So
daemon,
LXC
the hypervisor.
So LXC is a low-level implementation of a container stuff, but it's more like a toolbox. It requires a lot of manual configuration. Like it's one of the things that Nspawn was supposed to do right from the beginning, that you don't have to set anything up, you just point it to the directory and will boot it up. LXC was more like a toolbox. It required you to sit down, write a configuration file with lots of settings that are not easy to understand. And honestly, I think most of them make zero sense at all. But anyway, they ask you for that anyway. LXD now is something that the LXC people came up with, that is an application server sitting on top of LXC, right? So this is explicitly not what we want to do with this kind of stuff, because we will not do this orchestration application server thing that opens this up for the network. We will focus on the lower level things and get the lower level things right. So what Nspawn and these kind of things are really low level things. That we believe are done the right way. We do not, there's no competition at all with LXD stuff. You can say, if you really want to, that we compete with LXC, but not with LXD. Because LXC is this low-level toolkit, and we are also a little bit of a low-level toolkit, but we have nothing compared to LXD, and we have no intention to. I hope this kind of makes some sense. But honestly, I think if you use LXC, you probably can use Nspawn as well and have to configure less. But anyway, this is now me talking and telling everybody that Nspawn is so much better than LXC, but I don't know. The LXC people, of course, disagree. Other questions? No questions? Okay, then I'll, this slide I'll do then as well. I mean, it doesn't really matter if we do the slide or not. So one of the last things I would like to talk about is the stateless systems concept. So if you work for containers, then they have this benefit because they're very lightweight. They allow you to increase the density of how much you run your servers immensely. And this also means that you want to have a way that you can run the same container a million times, not only in the local system, but all across the system, all across your cloud. So since we are systemd, we kind of care for the lower level part of the operating system. So we thought, how can we make that easier? And one thing that we came up with there is stateless systems. Stateless systems are basically something where /user contains the entire operating system, everything that's needed to boot up, and /etc and /var can be flushed out completely, be empty, or actually be non-existent, so that they are reconstructed on first boot. So the idea being, you have one /user image, that's your golden image, and then every time you boot it up, and etc and var are empty, we reconstruct the minimal stuff that's necessary to make that work. It's actually like, if you flush out etc and var once, then you have basically something that we call a factory reset. So it's basically, I mean, we call it factory reset, like if you think of a mobile phone, right? The Android phones actually work very much like this. They have 3 partitions on them: state, configuration, and vendor, or so they call it. And if you go to the UI here and do a factory reset on the Android phone, it will actually flush out the configuration and the state partition and leave the vendor partition in, so that the next time you boot up, it will notice, oh my god, I have no state and no configuration, then it will show you the nice wizard so that you can add it again. So that's how factory reset works on Android. We kind of say we want the exact same thing on classic Unix systems, where /user is what Android calls vendor, where etc is what Android calls configuration, and where var is what Android calls state. So if you flush that out once, then you get a factory reset. But you can take it even one step further, where every time when the machine boots up, you get etc, var completely flushed out, and so you have a stateless system. Like, it's a system basically that boots up, does what it needs to do. When it's shut down, nothing remains. Right? This is incredibly useful for web setups, basically, where you traditionally, in a web setup, or nowadays in a web setup, you usually have a separation where you have a storage backend, which could be MySQL or some cluster file system, whatever you have. Then the nodes that actually calculates this stuff, and then a proxy in front that distributes the HTTP requests on it.
Or is FSTAP going
FS stop going. I mean, you can, we don't need it, right? Like, if you have a simple system where everything is contained anyway, you don't need that really, like, because you have to point the kernel on the image, and then the image can find the rest, right? Of course, I mean, if you want to have a complex setup where you have storage, external storage configured here and there, and things like that, then that's not really the model you should follow. This is really, like, very useful for embedded devices, but also for the container stuff that I'm kind of talking about here, right? So, yeah, for the classic setup where you have storage layer in the back, then the actual calculation node, like the processing nodes, and then the proxy in front, it's actually really, really useful because you can say, okay, now I want to start 500 containers, they come up without state, they will not store any state, and everything that I actually really want to save always goes back to the real backend of this stuff. So we built this on the systemd itself, and it actually works even on Fedora nowadays. It doesn't work for all packages, because many packages actually insist that etc is fully populated. But basically the basic operating system works this way already. We're trying to get Fedora to adopt the scheme fully, meaning that you can basically say, if etc is empty, that's an indication that the administrator has configured nothing. And everything that the administrator configures, he'll put in etc, so basically that etc and the administrator configuration are identical, right? Which is completely different from how Unix systems work most of the time right now, where etc contains a lot of stuff, and you never know, is it something that I configured, or is it something the vendor configured, or is it something that upstream configured? It's not clear. So we have support for these kind of stuff in, oh shit, wrong key. In systemd as well. So one thing that's actually really powerful then is if you have the same user and you use it on a ton of different systems, right? You just mount the same original golden image into a ton of different systems, and then you can either go for the stateless system stuff where everything else is completely stateless, or you can go for just a factory reset system, so that where the first time it boots up, it will reconstruct in etc and var what it does, but everything in the future will still, like every change you make in etc and var are going to actually stay persistent. But then by mounting the same /user into a lot of these images and updating this /user thing, you can in one step update 500 container instances, so that they will not have to be individually updated, but all at once simply because you updated /user. This is not always that trivial, simply because sometimes if you update /user, you need to make changes to etc because configuration files changes. So we provide you with some concepts there so that that works. But anyway, putting this together for containers is a big opportunity because it's not all round yet. It's not finished, this work in this area. But it kind of laid the building blocks so that we have a very, very clear separation between state configuration and the vendor operating system, and hence between what the admin added or what the runtime added, and from what the vendor added. And you can return, you can share the images, you can upgrade the images, all in a very similar way, in a systematic way. And actually, everything that this is about works the same way if you build a Linux phone, or if you build a container, and actually also if you build a server, things like that. It's all the same concept there. In systemd nspawn, support for this kind of stateless system is actually explicitly supported with the -- volatile script. If you want to know details, check the man page. So, what else can I say? I mean, I got like 3 minutes left. Anybody a question? I mean, these are really my backup slides in case nobody asks questions. So,
when will you have the stateless systems?
When? Well, it really depends. I mean, for simple ones, you can have them now, right? Like, if I take a simple Fedora, like that has no UI, but has all the really basic building blocks, I can boot it up without any like, and just like, and I delete etc and delete var and delete everything else except for /user, I can boot it up already. When you will have it like for real people, like so that it actually works with Apache and these kind of things, I don't know. We still need to convince Fedora that this is actually a good idea to have, right? I mean, let's not ignore the fact that this is what we think how it should look like, but of course there are a lot of people who really dislike the idea and say that, well, this is not Unix, and Unix etc was always filled with lots of stuff. But I don't know. I think that this makes a lot of sense, especially like we have a large tool set around this kind of stateless stuff. Like there's a command called systemd delta. And systemd delta basically, you know, Etsy traditionally had all these configuration files that the vendor or like the upstream vendor or the distro vendor thought would make a lot of sense, and they shipped them in Etsy so that the admin can go there, look at them, change them, and have the inspiration from the example that's already there, right? And by flushing out Etsy, you of course lose that. So we thought, okay, that would be awful if the admin would really lose that. So what we say is, yeah, this directory should exist still with the examples, like what you actually can put in Etsy. But we always ship a version of that in Etsy, in user lib factory. And basically so that the factory directory that there is has always the original versions by the vendor, and then systemd delta, this tool that I was talking of, has this nice functionality that it can compare basically the contents of user lib factory against Etsy, and this basically will give you like a diff output about all the configuration changes that you as an administrator made compared to the vendor defaults, the original ones. So it's actually a really, really useful tool. But yeah, we try to make this interesting for admins so that eventually this is a real benefit how you can work, because you can always know, I run my systems with the minimal amount of configuration necessary, and if I want to know what I actually changed there, I can do that at any time without having to figure, is that my change or is it their change, because you can always say systemd delta, and then you see exactly the changes that you made, and nobody else. But anyway, I'm out of time. These are my backup slides, so it doesn't matter that we don't do them, so let's go to the next one. Which is, that's all, folks. So thank you very much for your time, but maybe we have time.
I think we have some time for questions, so if anyone has one, feel free. Okay, so...
I need more questions, no questions. So if you have any further questions but don't want to ask them in the big audience, I'll be around in the corridors for anything else you might have. And thank you very much for your time.
Thank you very much. Dobrze, mamy parę minut przerwy i zapraszamy na ostatni wykład. Tylko czas damy prelegentowi, żeby się zainstalował.